Namaskar. Today we are going to discuss Picard's existence and uniqueness theorem. So this is very important topic in the context of differential equation. Basically, in all the competitive examination like NET and national level examinations, you can see there are always some questions from this theorem, Picard's existence and uniqueness theorem. And today we are going to discuss a statement, and we are going to also prove it step by step how we can prove Picard's existence theorem. Now, in Picard's existence theorem, whatever condition we are going to impose to on the equation so that the solution become unique and the solution exists, you will see all these conditions are not necessary, but they are sufficient for the existence and uniqueness of the solution. Necessary means there are not necessary means there are some there may be some differential equation where without satisfying this condition the solution exists. Okay, that we will also see at the end of the proof of this theorem. We will also discuss this type of examples where we will see that these conditions are not necessary but sufficient. So this is very important to remember this. All these conditions we are going to discuss in this theorem, these conditions are not necessary but it is sufficient for the result. And if it is not necessary, then there is always a scope for improvement to make it necessary. That means what is the minimum conditions that should be satisfied so that it become necessary. So we'll also we'll see all this discussion after the proof of this theorem. We'll also discuss all these conditions and how there is a scope of improvement the conditions of Picard existence theorem, and how we can improve it with less conditions, with less sufficient conditions. So with this summary, let's start today's discussion. So already the topic is differential equation and numerical solutions, and under this topic we are going to discuss this theorem. Okay, so as you can see the Picard's theorem, this is statement. So what we are doing here we have a first order differential equation, initial value problem. We say this is an initial value problem. Why? Because at the point of x0, the value of y is given, that is y0. So we have a first order differential equation. Okay, now we are going to discuss the conditions if which are sufficient for the existence of the solution, one, and second for the uniqueness of the solution. Okay, so basically there are two conditions. Let's discuss. This function y dash equal to f of xy, this f of xy should be continuous, okay, on an closed domain. Now here, as Picard have taken at this theorem, this domain is rectangle domain with parallel to the x-axis. Both the we'll also see the domain in the figure. So this is f have to be continuous on a bounded region, a bounded domain. Here this bounded domain is closed rectangle R. Okay, and the partial derivative of f with respect to y, that is del f del y, be continuous. This partial derivative should be also continuous. These are the conditions that have to satisfy. These are the conditions are sufficient for the existence and uniqueness of the solution of this equation. Okay, and formally they are saying if x0 y0 is a interior point of R, then now where this solution exists, they are giving you a region. That where we are going to find this solution, that is we are going to find this solution in a closed region around x0 y0 point, because x0 y0 point is our initial points. So this initial value are given, so we are going to find this solution around these points in a closed region. So if x0 y0 is an interior point of R, then there obviously this point have to be interior. Otherwise, how you can find out the value of y? Because the function f is defined on R. So if you want to calculate the value of the function at this point, to this point have to be interior, obviously. So you cannot take any initial condition at any point. If your point should be within the region. Okay. So if x0 y0 is an interior point of R, then there exists a number H0. H0 is a positive small real number, and using this H0 we are going to build a small domain around this point. Okay, that's why we are taking this H0 greater than 0 with the property that the initial value problem has one and only one solution. One and only means this is a unique solution. Okay, and where is the solution exists? In this interval, as I was saying, within the region, within a small region of x0, because x0 is our initial point, so the region should contain x0, and this is your region where we are going to find this unique solution. And once again, these conditions are sufficient, not necessary. Okay, all these conditions are sufficient for the existence and uniqueness, not necessary. Okay, let's move towards this figure. So if you see this figure, this is your domain R. This capital R is this is your domain, and this is your function. Now this is your actually solution, but we don't know this solution. We are going to find how we can see. Okay, so if this is your solution, this solution has to pass this point, and this solution will be within this region as per the definition of this equation. So this is our understanding. So what is R? This is R, and this is our Y. We don't know what is Y, but Y have to pass through this point, and it have to be within this region. So this is the figure we can draw from these conditions. Okay, let's, what is H? So we are using H, we are again constructing another region, a small region, taking x0, y0. So we are constructing another region taking x0, y0. Why? Because the function is defined on R, but sometimes it happens that all this property, beautiful property we are talking about, may not exist within the whole region. There is no problem. R1 can be R also. There is no problem. R1 can be R also, because we are taking R1. H is our, we are taking H. There is no restriction. H should be greater than 0. There is no restriction. So see, this is our H. Okay, so there is no restriction on choosing H. H should be 0. You can take H greater than as much bigger as you want, and you can make it equal to R also. But suppose in some cases your region is bigger, but you are not able to find all this condition, that is f of xy is continuous 1, and second is the partial derivative with respect to y of f is continuous, and these two conditions you are not able to prove in the whole region, but you are able to prove in a small region. Obviously, then at least, okay, we are not able to find the solution in the bigger region, but in a small region we will be able to find the solution. So that's why we are constructing this H. We are not initially, we are not starting with R. We are, okay, if we are not able to find in the whole region, then also our theorem will give you solution in a small region. Now H can be as big as you want. If all these conditions satisfy, you can take bigger H, no problem. Okay, so R1 will be, then in this case R1 will be R also. It can go bigger and it may be equal to R. Okay, now let's step by step see the proofs of this theorem. So initially, let me just give you hence the roadmap that how we are going to prove it. Just initially, let's construct a roadmap or a logical sequence that how we are thinking to prove this and using this whatever we have in our hand. Okay, so basically this is Picard's approach or Picard's way of proving this theorem. So what he has done here, what have done, that they have constructed a sequence of approximate solutions. Okay, so basically they have constructed a sequence. Basically, let's not get into that approximate solution. Let's see they are constructing a solutions. Okay, I'm not want to go into complexity in that. Let's go step by step. So they are constructing a solution such that this limit of this solution, that means the sequence where this sequence where it is converging, that will be our ultimate solution. So basically they are going to step by step. So what we will do, we will initially construct a sequence whatever we have in our hand, then using those existing conditions and properties, whatever given as a conditions in this theorem, we are going to show that this sequence is convergent. And not only that, where this sequence converges, that function is continuous. And again we are going to show that this function actually satisfy our given equation. That means this function is our solution. Okay, and ultimately we are going to show that this solution is unique. Basically, unique means we are going to take another solution, and we are going to show that these two solutions are not different, they are actually one. So basically we have one solution, that is the limit of this sequence. Okay, and we are going to assume that let's take any other solution, and at the end of the day we are going to show that these two solutions are not different, they are equal. So basically you have unique. You are not able to construct two different solutions. You are taking any solution, and ultimately you are going to show that these two are not different, they are same. So basically you have a unique solution. So this is our roadmap. This is how we are going to show. Now if you want to break it further more to understanding, so why I am doing it, before going to step by step proof, that is mechanical and logical, and we are going to use lots of mathematics here, we need to understand why we are doing it, so that you can make a flow, and if you want you can try on yourself also, could try to prove it by yourself also. So this is the roadmap. So this is how we are going to do. Okay, and you are going to use Weierstrass approximation theorem. So basically what we are going to, initially we are going to construct a sequence, then it is difficult for us to show that a sequence converges. Okay, so directly not proving that sequence, we are going to construct another series using this sequence, and we see where this sequence will be where this series will be sequence of partial sums for the series. That means the limit of the sequence and the limit of the series will be same. Okay, as we know, if we construct a sequence of partial sums from a given series, then both the limit are same, and if you show the sequence convergence or the series convergence, you can show that the series vice versa. So we are going to use that. We are going to first use a sequence. Our main motive is we are going to sequence in such a way that its limit should be our solution. Okay, then we are going to use this sequence to construct another series. Why? Because it is difficult for us directly prove that this sequence is converge. So we are going to prove that series is converged, and where this sequence is the sequence of partial sums of that series. So both the limit are same. Okay, that's the step on. Then okay, you have a limit point. Now you have a limit function. Now you have to show this function is your solution. So we'll just directly put it in our equation, and so it satisfies. Okay, next we are going to show uniqueness, as we have already discussed. So this is our roadmap. Now let's go through the steps. Okay, so as I have already told you, this is our differential equation initial value problem. Okay, initial value problem because you have a value given at a initial point x0. Okay, this is equation number 1. Okay, now we are, so see, there are small trick we are using in every steps. Okay, I have given you a bigger roadmap, but you will see at the end here small trick we are going to use, small things. Okay, so what you are using here, we are converting this equation into a integral equation. Okay, you don't understand integral equation. If you are not able to understand equation, just forget about this is integral equation, nothing else. You just take integration on both on side with the limit x0 to x. You will get this. We know how to do integrate. Okay, there is no problem with that. If you integrate, what will happen? Yx minus y0. I have just taken y0 in the right hand side. Okay, and if you take integration, this is we are getting. So you can convert this in this, no problem. Is a continuous. Already given f is continuous, we can already. So we will be able to integrate it. So is a continuous solution, the integral equation. Okay, this is called integral equation of this corresponding differential equation. Okay, but if you are not able to understand integral equation, let's forget it. Just see that I have taken integration on both the side, nothing else. Okay, but there is a standard result. Both the solution of this both the equation are same. And if this equation is given, equation 1 is given, you can convert to equation 2, obviously by taking integration. What you need f to be continuous because you are taking integration. That is sufficient condition, not necessary but sufficient. Continuity is sufficient, so we can integrate. And again, if y is differentiable, then you can by just differentiating 2 you can get 1. Okay, so to conversely we can convert it. We are converting it so that because we want to create a sequence, that's why I have taken integrations. Now we can thus say the equation 1 has unique solution on the interval if and only if this equation 2 has unique solution. Okay, that is clear. Let's move. So this is how, as I have already told you, this is how I am constructing a sequence. What is y0? This initial value. Okay. What is y1? The sequence of functions. This is sequence of function. This is y1, y0. So you how I have constructed, or Picard's, this is called Picard's method of successive approximation. This is not my thing anyway. So this is how they have constructed it. If you see, they are just using this equation 2. They are just using, you see every step they are just using this equation, and they are changing here, putting the previous approximation in here only. See, this is y0. Now they have put in y0 here. All the things are same here. Now again put y1 here. All the rest are same. This is y2. What will be y1? Says just yn minus 1 here. So this is your sequence. Now you can go on like this. So we are not ending here, it is going like this. So this is a sequence basically. Okay. So may converge to a solution. May converge. Why? May converge because we haven't shown that this sequence of function actually converge. So we are going to show that. Okay. Now, so yn is defined by this. May converge to a solution. So actually we are going to show this sequence is convergent, and is limit is actually solution of equation 2. Okay. Now here you may observe that yn is the nth partial sum of the series, as I was saying, but just modifying this sequence, just using this sequence, we have constructed a series such a way that this sequence become series of partial sums of this sequence of partial sums of this series. So basically this sequence is sequence of partial sums of this series. What does it mean? See, the first term of this series is your first term of your sequence. What is the second term of your sequence? The second term of your series is the sum of two terms of your series. Okay, so this is called sequence of partial sum, because this sequence has been built by taking partial sums of this series. So what will be the nth term? What will be the nth term of this sequence? First n terms, summation of first n terms. So if you take summation of first terms, all these terms are getting cancelled. You can see y0 get cancelled. So if you take just summation of 2 terms, you will get y1 like this. You can do the rest. If you y1 gets cancelled, y0 gets cancelled. So if you take summation of 3 terms, you will get y2 like this. You will get yn. Okay. Now and thus the convergence of sequence 3 is equivalent. Already this is standard result. This series will converge where this sequence of partial sums where this sequence of partial sum will converge. It's a standard result. Okay, we all know this in BSc from BSc mathematics. You can see this result in sequence of function and series of functions. Okay, equivalent. In order to prove this theorem, we are going to now prove this series is convergent. Okay, this is a smart way of just handling things. Okay, we are just directly not proving this sequence, we are proving this series. Okay, so what are the 3 things now we are going to prove? This series is convergence to a function, and this function yx, where this series converges, is a continuous solution, second, and this is the only continuous solution. So if we prove these 3, then our proof of the theorem is done. So ultimately the proof of this theorem converted to these 3 things we have to show. So first we are going to show this is convergent, then we show that this limit is our solution of this equation of the given equation, and finally we will show this is unique. Okay, now let's prove these 3 things one by one. We shall now prove the above three statements one by one. But first of all, let us try to produce a positive number is. Now again, we are going to play it smartly. We are going to do some modification, small things, so that it help us to prove this. Okay, so now let me tell you what is the roadmap to proving this convergence of this series. What is the roadmap? So what we are going to do here, we are trying to use Wester's M test. What is Wester's M test? So this series of function, we are going to show this series of function, every term is less than or equal to a constant series. Okay, and standard result of Wester's M test you can see in the series of function. Wester's M test, we can verify that. Okay, what is that? If series of function is bounded by a series of constant matlab real numbers, series of real numbers. Okay, that what is meant bounded means every term of this series of function is bounded by some constant. So every term of this series, we are going to show every term of this series is bounded by some constant, and the result is if that series of constant series is convergent, then this series of function will be convergent uniformly. Okay, and we know if it convergent uniformly, then the solution, if every term is continuous, then obviously the limit will be also continuous. So two things in a single steps, very smartly they have proved it. Okay, so that's why. Now what are, so we are going to show this, we are going to show these terms are bounded by some constants. So if you want to show these terms are bounded, now we are going to use whatever we have in our hand. We have already have this f and del f del y are continuous in a bounded domain. This rectangle domain is bounded, okay, closed bounded domain. And we all know if the function is continuous in a closed bounded domain, then since R is closed, see this is highlighted, R is closed, that is includes its boundary and bounded. So if continuous function is if a function is continuous on a closed domain, then automatically it become bounded. Okay, so this function is bounded and del f del y also bounded. We are going to use it to show them bounded. The terms of the series are bounded. Okay, so without any loss of generality, they are assuming, so let m and m are two constants, so that this is bounded by m and this is bounded by n, and they are already show that they are bounded from the initial conditions. Okay, from the given conditions. Now again we are going to use it. So see smartly what you are doing. You are doing all these things as per this. Here is a difference. Okay, and if you see their definition again, put this, here is this. So ultimately if you take integration common, you will get the difference of this function at y0 comma y1. So this is the back calculation. So first we are going to show this, and we are going to using it. Okay, so now f is obviously f is continuous, and the derivative of f with respect to y exists, that is again continuous. So it satisfies all the conditions of mean value theorem. Okay, so this should be this. Okay, so this by this should be equal to with derivative with respect to. So Lagrangian mean value theorem, we standard result. So there exists some y star between y1 and y2 such that this will happen. This is very standard result of Lagrangian mean value theorem. If a function, if a function is continuous in a closed domain and differentiable in a open domain, then f of y1 or f of x1 minus f of x2 by x1 mod of x1 minus x2 equal to the derivative of that function at some point within the interval x1 comma x2. Okay, so that they have used for y, and x here, x is acting as a, x has no role here, x acts as a constant. Okay, nothing, x has no, so we are just assuming this is a partial. So as we have taken partial derivative, so we are just considering here, we are doing all these things with respect to y. Very standard result. Okay, now again we have already shown this is bounded by n, so just put this, you are getting this. Now we are going to use it. Okay, Now they are smartly playing ace. Here is a ace. We have already seen in the theorem there is some ace. Here is a ace. We are smartly playing. We are taking n is any constant. Now what is n? How all the what are the condition we are going to imposing on n, that we will see later. Now so obviously whatever is your ace, you can obviously n is, you can multiply some real number n and make it less than 1, but it's very easy. Suppose this is less than 1, or you are dividing by 100 or whatever. Okay, so n is your real number, that is the only positive real number, that is the only condition. Okay, so and then rectangular, so n we are going to trying to find out some m, that's why we are putting this. This is a smart play, nothing else. So ace is given or ace is something, we are just assuming it. So you have already have shown you in the picture domain what is ace, and here is we are taking another integer and multiplying it with ace to make it less than 1. Okay, this multiplication less than, nothing else. So this is the domain of ace and this is the domain of y. So already x minus x0 less than equal to ace, this is the domain. And now how we have created a rectangle R1, this is how we are creating this R1. R1 is defined by this inequality, this and this is content in R, as this is the interior point of R, we can say such that such an ace exists. Okay, well, let's move. Now after choosing ace, we shall now prove the statement 1, 2, 3. So whatever you have done till now, you have just created something so that we can use it to prove the statement on here onwards. Okay, so if you see, this is your series of partial, this is your series. Okay, so it is sufficient to show that this series is convergence, and to achieve this we estimate these terms. So as we have already told you, we are going to use OS M test. So we are going to estimate each term by a constant. Okay, this is the bigger picture after this modification. So this is the new domain where this is already, we have already this interval of h0. Now we have created an interval of y0. So what is y0? From here to here. How we have taken y0? By some modification, mh. So from this figure you can see what is mh. So here is something y0, here is your y0, and this is a y minus mh, this is y plus mh. This is what m is what, del f del y is bounded by m, already you have assumed that. Okay, this not del f is bounded by m, so that m we have taken. So this is our freedom. So how we are constructing in rectangular domain with around x0 y0, this is your freedom, but it should be contained within R. That is the only restriction. So I have all the freedom to choose h and m's. So basically I am choosing two interval, one is around x0, another is around y0, so that this rectangle domain I can construct this triangle domain. So okay, so this is the figure. Okay, so here let's take a break, and after that we will show all these proofs, and then we will see some examples. Thank you.
Do you wish to be part of a television studio like this, or any other media system, or already part of any media system, want to enhance a new set of skills? Welcome to School of Journalism and New Media Studies. Here in the School of Journalism and New Media Studies, we are offering program for all set of people to learn and enhance their media skills. The vision of School of Journalism and New Media Studies is to generate a new set of professionals in the area of media and communication studies with understanding about role of media in the national development and global understanding. We offer innovative programs in the field of journalism and mass communication that sets a benchmark of high quality learning and teaching process at the national level. We offer these programs across the country with the help of our regional network as well as study center. Same manner, many of our programs are offered through online mode with a sophisticated learning management system. SOGNMS offers programs from PhD in Journalism and Mass Communication till certificate level. We have Masters in Journalism and Mass Communication. The eligibility is a bachelor's degree, and we are introducing this program in 3 languages: Hindi, Tamil and English. Students from national and international students can join either through online mode as well as in the distance mode. We have 4 postgraduate diploma programs, specialized areas in the field of development communication, digital media, electronic media and journalism and mass communication program. And all these 4 programs are available in distance mode. 2 programs are available in online mode, development communication and digital media. And we have specialized certificate program in community radio. IGNOU employs various media and communication tools for better teaching and learning process. School of Journalism and New Media Studies utilizes this media system for delivering all our programs. Come and join with us for exploring a new career and enhance your media skills.
Are you a fresh graduate? Do you want to fulfill your educational aspiration by pursuing higher education in various interdisciplinary and multidisciplinary areas like environmental science, environment and occupational health, philosophy, sustainability science, folklore and culture studies? If yes, the School of Interdisciplinary and Transdisciplinary Studies offers various programs like Master's Program, Graduate Program, Postgraduate Diploma, Certificate and Appreciation Program. The school offers 5 Master's Program: Master of Science, Environmental Science. The eligibility criteria for MSc Environmental Science is Graduate in Science, BTech, BE, Agriculture Graduate, Forestry Graduate and Veterinary Graduate.
Namaskar, welcome back to the session. Okay, let's start from where we have left it. Okay, so this is the domain. This is the domain that we have constructed by choosing suitable age and MAs. This age and MAs has been chosen as per our convenience. Okay, the only restriction is that your R1 should not exceed R. It should not go outside of your given region. So within this region I can construct another region as per my convenience. Okay, so that's how this H and MS has been chosen. Obviously M is what? M is dependent on f of x y. So we have already assumed that f of x y is bounded by M. So that's why this type of region has been taken, so that in future we can use it. Okay, so now this is bounded by M as I was talking. Every x, f of x comma y is bounded by M for all x comma y. So obviously this is also bounded by M. So y mod of y1 minus y0 is bounded by mh. Okay. So what is the maximum length? x0 to h. Max. You see the figure. x0 to h. Maximum length what? H. So for any point, what is the distance? Less than h. Maximum x0, how much you can go? You must go maximum h distance in the right, you must go maximum h distance in the left. So what will be the maximum distance for any point in this region from h0? That is h. So any point, if you take any point in this region, that x0 minus h, mod of x0 minus h will be always less than h. That is the definition of this domain. So what that is? So this is constant bounded by M. If you use it, so it will go outside of this integration, and this integration will be obviously x mod of x minus x0, and that is less than h. So this is bounded by mh. So see, this is how I am planning to show. This is my each term of my series is bounded by some constant. Okay, this is the first one. Let's see step by step. Again, y0 minus y2 is, so similarly we can show up to this y3 minus y0 and so on. Now so this is what I have done. I have taken y0, subtracted by y0 from each term from my sequence, and I have shown they are bounded. Now I am going to the nth term of my series. This is my nth term of my series. If you see the series, this is my nth term of my series, and now I am going to show this is bounded, just putting h0 in between them. So I will subtract h0 and add y0, just putting y0 in between them, so that I can use this result. Okay, very smart play. So see, they have just, okay, they have taken alpha maximum of this already. All of them we have shown these are bounded, so they are just doing all this modification. Let's go to the main step. Okay, so this is the term of my series. Okay, so this is there. This is, and again y1 minus y0 we know that is mh, and m is again they have shown this alpha. So they have used all these things. Okay, let's go. We know that a continuous function has a maximum on a closed interval. Since we have already seen the FD continuous function on a closed interval is bounded. So if it is bounded, it has a maximum. Since y1 is a continuous, we can define alpha by this and this. What is y1? Y1 is the second term of my sequence. Okay, so they have shown that y1 minus y0 is maximum this. So they are just going to use it in future. Okay, our aim is to show this is less than equal to some constant. Now again this point T1, this, and this is using this we have already shown for any 2 point. This is bounded by this by using Lagrangian mean value theorem on f. We have shown this. Okay, now this is bounded by alpha, so this is less than n alpha. Again this is, so this is again alpha into nh and going on. Okay, so just if you move forward to the sequence to the series for each term, there is just increasing on n and going. So this is how the nth term is less than equal to this. So continuing this way, we find that the nth term of this series, yn minus 1 mod of this thing should be less than equal to this. Okay, now continue. So what will be our series of constant terms? This is our series of constant source. The first term, that is same, both as we have taken the first term of my given series that we have constructed is was y0. So again we have taken here y0, and we have put we have just used there for each term we have used their boundary value. Okay, we have just shown that each term is bounded by this. So this is our series of constant term. Now we can use Weierstrass M test. So if this series is constant, this series is convergent, so by using Weierstrass M test we can show our series that we need to. That means the proof of 1 will be completed. That is how they are showing. So series 10, this series obviously you can see this series. We have assumed n such a way this is less than 1. So obviously this series is going to be convergent. This test convergence by comparison test, hence it is hence this series convergence to a sum which is denoted by yn. So we are assuming this series converging on a term that is yx. Thus yn converges to y. Also, since the graph of each yn lies in R1, the graph of y also has this property. So this completes the proof of statement 1. And West's, as from the statement of West's M test, we know this is not just convergent, it is convergent uniformly. And since uniform convergence is there, so if each term of your series of function is continuous, then your limit will also be continuous. Okay. So from there we can calculate y is continuous also. That is what they have also said. So next, to prove statement 2 from the proof of 1, it is clear that not only yn converges to yn converges to y in the interval, but also this convergence is uniform. Since yn is each yn is you can see the definition of yn, it is continuous. So just let me show you. What is our definition of y? N, this is our yn. So f is continuous, you are taking integration, so obviously after integration it will also become constant. This is just constant, so each yn is continuous. And what is this? You are just difference up to continuous function, so again it is continuous. Okay, so each term of the series is continuous, so obviously the limit will be also continuous as the convergence is uniform. Okay. Okay, let's move forward. So statement of 1 is complete, that we have shown that series is convergent. That is our first part of this proof. Statement 2, to prove statement 2, we have shown that y is continuous. Okay, as it is uniformly convergent, so and each term is continuous, so the y is also continuous. Now we are going to show that this satisfy the equation 2, that is the equivalent equation of our given equation. So just taking integration on both the side of the given equation, we have constructed equation 2, if you can remember. So we will just show that this y satisfy our equation. So obviously it will be a solution. This is our aim to show here. Okay. So yx minus y0 and this. So how to show that? Just to prove that their difference is 0. This is what was your equation, y equal to y0 plus this. Okay. So I am showing this satisfy. So y satisfy this equation. This is our aim. So to prove y is actually solution of equation 1, we must show that this equal to 0. Okay. From this relation, we know that this is our definition of yn, nothing else. If you see, this is a definition of yn. They have taken y0 and this in the left hand side, nothing else. Okay. So now take limit on it. If you take limit, so this is this. If you see if sum, so just subtracting left hand side. They have subtracted this left hand side of 12 from 11, and they have got it. Then they will take limit. Okay. The modification by taking modulus on both sides, we obtain this. Since the graph of y lies in y1 and hence r is using the relation, we must have this. So just simple calculation. This is the simple calculation after subtraction. They have taken modulus. This is we can write this, and then after subtraction they have taken modulus. So mod of a plus b less than or equal to mod a plus mod b. So this is happening. And then this is less than or equal to NAs, we have already seen, and this is max of this. So this term can be approximated by this. Okay, very simple. By what? By f, or already shown that by using Lagrangian theorem. Okay, mean value theorem on f. This difference is f of this difference. So there is 2-3 steps done in a single time. you can verify it, okay, very simply, just using Lagrangian theorem. I have already shown Lagrangian theorem for f, we are just using those result here, okay. So this difference will be less than equal to n into mod of yn minus 1 minus mod of yn minus 1 minus y, and so this will happen, okay. So the uniform convergence of yn to y implies that the right hand side of the inequality 13 can be made as small as we place by taking large in large theorem. So again, so if you take n, so if you take limit, this n will go close to y, because y is the limit of yn, okay. So the right hand time, all this again, this yn minus 1 also will go to y. So the right hand time will, the right hand side will vanish, will go to as close as 0. So obviously the left hand side should be equal to 0. That is the conclusion we can make here. The uniform convergence of yn to y implies the right hand side of the inequality can made as small as we can place by taking n large enough. The left hand side of the inequality must therefore be equal to 0, and this completes the proof of statement 2. And statement 3, they have assumed that let y bar is another solution. Then they will show that if y bar is a solution, y bar have to lie in within R1. Otherwise, it will be a contradiction. So what we are assuming y1 does not leave R1 for this whole interval x0 to x0 plus h and x0 minus h. So x0 minus h to x0 plus h. In the whole region or domain of x0, y1 should not leave the y bar is another solution. I am assuming, as I have already discussed the roadmap that we have taken, we will assume that y bar is another solution, and ultimately we will show that y bar and y are equal. This is what we are going to show, okay. So first assumption is it cannot live. If it live, okay, if possible let live, it's live at x0 point. So after x0 it is leaving R1, it is going outside of this region of y at the point x0. x0 is the last point. After this point, all the value of y bar are going outside. All the value of y are going outside of this region. It actually we are going to show this cannot happen. If this happen, we are going to see the constant. Simple. X0 be such that, so this is our assumption, x0 be such that this is x0 within the region, but y bar is equal to mh, and obviously after this point it is leaving mh, okay. So from this we can just divide both sides. This is equal to m. So y bar x1 minus y0, but just they have divided both sides of this by x1 minus x0, okay. Now this is obvious, this is less than h, so in the denominator it is h is bigger, so the whole thing will be less. So this is less than mh by h. So we are showing this ratio is greater than m, okay. Simple calculation just by dividing both sides by this, okay. But by mean value theorem you can see this denominator is less than m. This is simple mean value theorem, Lagrangian mean value theorem, basically y bar, obviously y is have to be solution, so it is continuous and is derivative, all these things that we have assumed satisfy f, okay. So all these things will be here also. Solution and satisfying differential equation, so have to be differential, so differentiable, it have to be differentiable, so differentiable and continuous, so we can apply mean value theorem. So by mean value theorem, so this is two contradictory thing. Here we are showing this is greater than m, here we are showing this is less than equal to m, the same thing, okay, this same ratio, so contradiction, so it cannot leave R1. So first is same. Second, we are going to just use the previous inequalities and we are going to show these two things are same. That means these two things are less than equal to this. So this if you just subtract them, you will get this. Just put, it's a solution, so it's to satisfy the equation, they put just and just take in subtraction both sides. So y bar minus y equal to this, very simple, just put y bar and y in the equation and take the subtraction. y0 get cancelled, you will get this, okay. Now this is we have already assumed in as equation 8 we have already assumed after applying mean value theorem on f. Okay, so using this right hand side is less than equal to this. Okay, now maximum of this is less than equal to maximum of this. This implies this is equal to 0. How? Okay, so maximum of this is less than equal to this for all the values. So maximum of this will be also less than equal to this, right? So this is what they have shown. Maximum of this is less than equal to this. Now these are same. These are same. If these are same, if we are able to cancel it, what will happen? NAs will be greater than 1. NL will be greater than, but our assumption was what? NAs is less than 1. Contradiction. So if you cancel it, if you are able to cancel it, otherwise this will be greater than 1. It's contradiction. So you cannot cancel it. So how, only one situation you are not able to cancel it if it is 0. So otherwise we will have contradiction. So that's how we have shown uniqueness of this Picard's approximation, Picard's uniqueness and existence theorem. So this is unique. So at the end of the day, we are showing y bar and y are both the same as per our roadmap. Okay, so this completes the proof. Now let's see some remarks. Okay, as I was discussing, the Picard's theorem is sufficient but not necessary. If it is not necessary, so there is obviously a scope for improvement to make it necessary, right? So is there any lighter condition which we can put so that then also solution will exist? Obviously, some functions are escaping our conditions. By escaping also they are giving unique and exist solutions. Okay, solution exists and giving a unique solution also, as these conditions are not necessary. Okay, so what we can do? So first remark, Picard's theorem can be strengthened. Obviously there is a scope for modification, as I have already told, as it is not necessary, so obviously there is a scope for modification. So Picard's theorem can be strengthened in various ways by weakening its hypothesis. For example, our assumption that del f del y is continuous. Okay, instead of taking this, you can take Lipschitz condition. Okay, so all these things I have discussed here on R. So then prove inequalities. So but in the proof you will see actually we have used it to create mean value theorem. We have used it to use mean value theorem on f. That means Lagrangian mean value theorem, and that ultimately gives you what? That ultimately gives you a Lipschitz condition. That ultimately. So basically we have used this in the proof. If you see the proof carefully, we have used this. We didn't use this condition directly. We have used this condition to make this conclusion, but this conclusion is lighter than this condition. Okay, that means del f del y implies this condition, but this condition is not necessary to satisfy. Okay, so to be a partial derivative with respect to, so this is lighter condition. So in simple, this condition is lighter. We are going to show this with example. So this condition is called Lipschitz condition. Lipschitz condition is lighter condition than the derivative have to be continuous. The derivative of f with respect to y have to be continuous. This was our condition. So we can drop this condition and we can add this condition to make our make our theorem more better by lightening your conditions. You are losing some conditions. Then also you can use it. That then also it will be sufficient. Okay. So then it will include more functions. So it called Lipschitz conditions. Okay, let's see. If we drop Lipschitz condition, now what will happen if we drop Lipschitz condition and assume only this is continuous? So if we take only f of xy is continuous, then also solution will exist, but uniqueness will not be guaranteed. Okay, this result is known as Pioneer's theorem. Okay, after the name Italian logician and mathematician Giuseppe. But this is only but with this only this assumption of solution with the existence theorem guaranteed but not unique. Okay, so what will happen? Our theorem have two conditions, that is f have to be continuous and del f del y also have to be continuous. Now if you drop the second condition, then also the solution will exist, but there is no guarantee of uniqueness. Okay. Now as I was discussing, if you see this example, y dash equal to 3, 2 by 3 with this, okay, in this rectangle, then this is a continuous on this, and in this are two different solutions. So as I was discussing, this doesn't satisfy ellipsis condition, you can verify it. Okay, then you have two different solutions. Here this is a continuous on R also, this is and this. So y1 equal to xq and y2 equal to x0 are two different solutions of this problem, valid for all x. Okay, this is your, so here f of xy is this 3, y 2 by 3. But that means this equation has two different solutions, not unique. Because why? Because this function doesn't satisfy ellipsis condition. Okay, so it is not guaranteed unique solution if you drop this. But sometime it happen also, the ellipsis condition doesn't satisfy, but you are getting unique solution, as this is not necessary sufficient. Okay, so this is what we have shown, this function is not satisfying ellipsis conditions. Okay, remark 3, local existence and uniqueness theorem, because it's guaranteed the local unique solution on this interval. Okay, if you take this type of linear equation, you know already linear equation. Okay, then px and qx are continuous is enough. Not only this first order, any nth order linear, if you take any nth order linear differential also, then also only the coefficient, if the coefficients are, since here we are talking only first order, that's why I have taken the example of first order only. If you take this type of equation, then the ellipsis condition will be automatically satisfied. Px and qx are continuous, then the ellipsis condition will be automatically satisfied. So there is no need of imposing second condition, that which is automatically satisfied, or verifying it. Okay, so the only condition we need, px and qx are continuous on this interval. Okay, and we have shown f of xy satisfy ellipsis condition automatically. Okay, doesn't need to write it separately, only conditions. And here is another example. If some function satisfy ellipsis condition, that doesn't imply you have to be differentiable with respect to y. That means ellipsis condition is lighter than del f del y is continuous. Okay, so here we have shown, if you take f of xy equal to x square mod a, obviously it will satisfy ellipsis condition, since there is modulus, so what is obviously it will not be differentiable at the point 0. Okay, so it failed to exist del f del y, but it satisfies ellipsis condition. So if you take the lighter condition, ellipsis condition, instead of taking Picard's conditions for del f del y have to be continuous, then your sufficient condition become lighter. Okay, and here they have shown, okay, this satisfies ellipsis condition, but the derivative doesn't exist. And here we have some other examples, but here we are going to stop it. Okay, so this is what we have done. We have seen the statement of Picard's existence and uniqueness theorem, and then we have discussed the proof step by step, and then we have seen how we can improve the conditions, and we have also seen the examples, and we have, most importantly, we have seen this is necessary but not, sorry, this is sufficient but not necessary. Okay, thank you. Namaskar.